Welcome to today's session. In this problem, we will explore an exciting challenge titled Sort Characters by Frequency. This problem tests your ability to work with string manipulation, frequency counting, and sorting algorithms. Let's dive in and break it down step by step. In this problem, we're tasked with sorting the characters of a string based on their frequency of occurrence, in decreasing order. This means that characters that appear more frequently in the string will come first in the output. If two characters have the same frequency, their relative order in the result does not matter, so there can be multiple valid outputs. The input is a single string S, which contains only printable ASCII characters. The output is also a string, where the characters are arranged as described. For example, if the input is the string S equals tree, the output would be ERT because the character E appears twice, while R and T each appear only once. Notice how E is placed first due to its higher frequency, and the order of R and T can vary since their frequencies are the same. Now, let's look at another example. If the input string is S equals caca, the output is caca. Here, the character C appears 3 times, and L also appears 3 times. Since both characters have the same frequency, their relative order in the output doesn't matter. Thus, AAC would also be a valid output for this case. Another example is S equals AB. In this case, the output is BBAA because the character B has the highest frequency, appearing twice, while A and A each appear once. It's important to note that the input is case-sensitive, so uppercase A and lowercase a are treated as distinct characters. Finally, let's consider the constraints and edge cases for this problem. The string S can have a length ranging from 1 to 500,000, so our solution needs to be efficient enough to handle very large inputs. The string may include English letters, both uppercase and lowercase digits, and other printable ASCII characters. For edge cases, consider a string with only one character, such as S equals A, the output would simply be A. If all characters have the same frequency, like in S equals ABCD, any permutation of the input string is a valid output since all characters occur exactly once. Lastly, remember that the function must account for case sensitivity, treating uppercase and lowercase letters as distinct, and it should efficiently handle large strings near the upper constraint of 500,000 characters. When considering how to solve this problem, a straightforward idea might be to use a brute force approach. The intuition here is simple. First, count the frequency of each character in the string using a dictionary or an array. Then, manually sort these characters based on their frequencies, and finally, concatenate the characters repeatedly according to their counts to form the final sorted string. However, this method has significant drawbacks. The manual sorting and repeated string concatenation make it highly inefficient for larger inputs, leading to a time complexity of O(n) squared, where n is the length of the string. Additionally, while it only requires O(n) space for storing frequencies, the high time complexity and error-prone manual steps make this approach unsuitable for practical use cases, especially when dealing with long strings. A more efficient solution involves leveraging Python's built-in tools and data structures. Specifically, we can use a hash map to count character frequencies and then take advantage of Python's sorted function to sort the characters based on their frequencies in descending order. The process starts by using collections counter to quickly calculate the frequency of each character. Next, we use sorted with a custom sorting key to order the characters by their frequency. Finally, we construct the result by multiplying each character by its frequency and joining the results into a single string. This approach is significantly more efficient, with a time complexity of O(n) plus k log k, where n is the length of the string and k is the number of unique characters. It also requires O(n) plus k space for the hash map and the result string. By taking advantage of Python's optimized sorting and concise syntax, this approach strikes a balance between efficiency and simplicity. Another alternative to sorting the characters directly is the bucket sort approach. Here, instead of sorting, we group characters into buckets based on their frequency. First, we use a hash map to count the frequencies of each character. Then, we create an array of buckets, where the index of each bucket represents the frequency, and the bucket itself stores all characters that occur with that frequency. To construct the final result, we traverse these buckets in reverse order, from the highest frequency to the lowest, adding characters to the result string based on their counts. This method has an optimal time complexity of O(n), since both frequency counting and bucket traversal are linear operations. It also uses O(n) space for the hash map and the buckets. However, despite its efficiency, this approach is less intuitive to implement and may be harder to understand and maintain compared to using built-in sorting. The strategy we ultimately chose is the optimized approach using a hash map and built-in sorting. This method balances simplicity, efficiency, and readability, making it a practical choice for this problem. The key insights are that using a hash map allows us to efficiently count character frequencies in O(n) time, while Python sorted function provides a straightforward way to order characters by frequency with a time complexity of O(k) log k. Additionally, constructing the result string through character multiplication and joining is intuitive and efficient. While the bucket sort approach offers an optimal time complexity of O(n), its additional implementation complexity and less intuitive design make it less appealing. On the other hand, the brute force approach is far too slow and cumbersome for large strings. By choosing the hash map with sorting, we achieve a solution that is not only efficient but also clean, maintainable, and easy to understand, making it the best overall choice for this problem. To solve the problem of sorting characters by their frequency, we need to start by understanding the problem setup. The goal is to count how frequently each character appears in the input string and then sort these characters in descending order of their frequency. If two characters have the same frequency, their relative order from the original string must be maintained. This is known as stable sorting. The first step in our algorithm is to initialize a frequency counter. Here, we'll use a dictionary, which allows us to map each unique character to its frequency efficiently. Dictionaries are ideal for this task because they offer O(1) time complexity on average for insertions and lookups. The process involves iterating through the string, and for each character, we either increment its count in the dictionary or initialize it with a count of 1 if it doesn't already exist. For example, if the input string is abc, our dictionary will end up looking like this: A2, B3, C1. This frequency dictionary forms the foundation for the subsequent steps in the algorithm. Once we have the frequency dictionary, the next step is to convert this data into a more sortable format. Specifically, we transform the dictionary into a list of tuples, where each tuple contains a character and its frequency. This is important because sorting a list of tuples is straightforward and allows us to define a custom sorting key. To achieve this, we iterate through the dictionary and append each key value pair as a tuple to a new list, which we can call frequency_list. For instance, using the earlier dictionary, A2, B3, C1, the resulting list would be A2, B3, C1. Now that the frequency data is in a list, we move on to the sorting step. Here, we sort the list of tuples based on the frequency values, ensuring that the order is in descending order. By using Python sorted function and specifying a custom key, we can achieve this. The key for sorting is set to the negative of the frequency, which effectively sorts the values in reverse order. Stable sorting ensures that characters with the same frequency retain their input order, which is critical for correctness. Python sorted function is stable by design, meaning that when two elements have the same sorting key, their relative order from the input is preserved. This property is particularly useful for our problem, as it ensures that characters with equal frequencies maintain their original order from the input string. After sorting the frequency list, we can move on to constructing the result string. The goal here is to create the output string by repeating each character according to its frequency. To do this, we initialize an empty string and iterate through the sorted list of tuples. For each tuple, we append the character repeated by its frequency to the result string. In Python, this operation can be efficiently handled with the join method, which avoids the overhead of repeatedly concatenating strings in a loop. For example, if the sorted list is B3, A2, C1, the resulting string would be Babak. This step ensures that the output string is constructed in the desired order, meeting all the problem's constraints. Looking deeper into the algorithm, there are several key insights that highlight its efficiency and correctness. First, the use of a dictionary for frequency counting is deliberate because of its O(1) average time complexity for both insertions and lookups. This ensures that counting frequencies in a string of length n is an O(n) operation. Second, Python sorted function plays a pivotal role because of its stability. Stable sorting guarantees that characters with the same frequency retain their original order, which is crucial for solving this problem accurately. Finally, constructing the output string using the join method is both concise and efficient. Unlike concatenating strings in a loop, which would lead to higher time complexity due to the immutable nature of strings, join avoids this overhead. Regarding data structures, the dictionary is used for frequency counting, a list of tuples is used for sorting, and the resulting string is the final output. Each of these structures is chosen to optimize for efficiency and simplicity. These choices contribute to the overall robustness of the solution. Analyzing the algorithm's complexity, the time complexity is primarily determined by the steps of frequency counting, list conversion, sorting, and output construction. Frequency counting operates in n time, where n is the length of the input string. Converting the dictionary to a list of tuples takes k time, where k is the number of unique characters. Sorting this list has a time complexity of k log k, and constructing the result string by iterating through the sorted list is an n operation. Combining these, the overall time complexity becomes n plus k log k. The space complexity is also efficient, with the dictionary requiring k space for storing frequencies, the list requiring k space for tuples, and the result string requiring n space. Thus, the total space complexity is n plus k. Finally, it's important to consider edge cases. For an empty string, the algorithm should return an empty string. For inputs where all characters are identical, such as AAAAA, the algorithm should correctly handle the frequency sorting. Similarly, single character inputs like Z and mixed frequency inputs like AB need to be processed accurately to ensure the solution is robust and handles all scenarios gracefully. This Python implementation solves LeetCode problem number 451, sort characters by frequency. The goal is to sort the characters of the input string based on their frequency in descending order. Step-by-step explanation. 1. Import required library. We begin by importing counter from the collections module. The counter class is used to efficiently compute the frequency of each character in the string. 2. Count frequencies. The frequency variable stores the frequency count of each character in the input string. For example, if the input is tree, frequency will be T1, R1, E2. 3. Sort characters. The sorted function is used to sort characters based on two criteria. Primary criterion, characters are sorted by their frequency in descending order, using frequency, x. Secondary criterion, if two characters have the same frequency, their original order of appearance is used, ensured by the stable nature of Python sort. For our build result string, using a list comprehension, we repeat each character according to its frequency and join the results into a single string. For example, if sorted _chars is ETR, the result becomes ETR. 5. Return the result. Finally, the constructed string is returned as the output. Complexity analysis. Time complexity. Counting frequencies takes n, sorting characters takes k log k, where k is the number of unique characters, and building the result string takes n. Overall, the complexity is n plus k log k. Space complexity. The solution uses k additional space for the frequency dictionary and n for the result string, leading to n plus k in total. This implementation is efficient, concise, and handles edge cases like empty strings or strings with all unique or identical characters correctly. Here, we start by importing the necessary Java utilities and defining our class solution. Within it, we implement the frequency sort method, which takes a string s as input. The first step is to count the frequency of each character in the string. To do this, we use a hash map where the keys are the characters and the values represent their frequencies. As we iterate through the characters of the input string using a for loop, we update the map by either incrementing the existing count or initializing it to 1 if the character is not already in the map. Once we have the frequency map ready, the next step is to sort the characters by their frequencies in descending order. To achieve this, we create a list of the map's key set and use a custom comparator. The comparator first compares characters by their frequencies, and if two characters have the same frequency, it falls back to sorting them lexicographically, in ascending order. This ensures that the sorting criteria are strictly defined and consistent. After sorting, we move on to constructing the result string by repeating each character based on its frequency. Now, we use a string builder to efficiently build the result string. For each character in the sorted list, we retrieve its frequency from the map and append the character to the string builder as many times as its frequency dictates. This is achieved with a nested loop, where the outer loop iterates through each character in the sorted list, and the inner loop handles appending the character the required number of times. Once all characters have been processed, the string builder contains the final result string, where characters are ordered by frequency and lexicographically for ties. Finally, we return the result as a string using the toString method. This approach ensures that the solution is both efficient and adheres to the problem's requirements. To solve this problem, we start by counting the frequency of each character in the input string. For the example s equals tree, we use Python's counter from the collections module to get the frequency of each character. The result is t1, r1, e2. This tells us that the character e appears twice, while t and r each appear once. Next, we sort the characters based on their frequency in descending order. To do this, we use a sorting function with a lambda expression. The lambda sorts by two criteria: first, by negative frequency so that higher frequencies appear first, and second, alphabetically to break ties for characters with the same frequency. After sorting, we get E, R, T. Here, E comes first because it has the highest frequency, and R appears before T due to alphabetical order since both have the same frequency of 1. Now that we have the characters sorted by frequency, we can build the result string. For each character in the sorted list, we repeat it according to its frequency and concatenate the pieces together. For example, E appears twice, so we repeat it to get EE. Similarly, R and T each appear once, so they become R and T respectively. Concatenating these gives us the string ERT. This is the final result for the input s equals tree. The most frequent characters appear first, and ties are resolved alphabetically. In the second example, the input string is s equals caca. First, we count the frequency of each character, resulting in C3, A3. Both C and A appear 3 times. When sorting the characters, we again use the lambda function that sorts by negative frequency and then alphabetically. Since both characters have the same frequency, they are sorted alphabetically, which means it comes before C. The sorted characters are A, C. To build the result string, we repeat A 3 times to get AAA and C 3 times to get CCC. Concatenating these results in the string AAC. This is the final output, with characters sorted by frequency and ties resolved alphabetically. For the third example, the input string is s equals ab. First, we count the frequency of each character, which gives us ab1, ab1, b2. The character b has the highest frequency, appearing twice, while a and a each appear once. Next, we sort the characters using the same criteria. B comes first because it has the highest frequency. For a and a, since they have the same frequency, they are sorted alphabetically, with uppercase letters coming before lowercase letters. This results in the sorted list B, A. To build the result string, we repeat B twice to get BB, A once to get A, and A once to get A. Concatenating these gives the string BBAA. This is the final output for the input s equals ab. To analyze the time complexity of this solution, we break it into 3 main steps. First, counting the character frequencies using the counter s function involves iterating through the string s of length n. Each character in the string is processed exactly once, so this step runs in n time. Next, we sort the characters by frequency using the sorted function with a custom key. The sorting step considers k, the number of unique characters in the string. Since timsort is used, the complexity of sorting is k log k. However, since k is at most equal to n, in the case where all characters are unique, the sorting step has a worst-case time complexity of n log n. Finally, constructing the result string involves repeating each character according to its frequency. The total number of repetitions across all characters equals the length of the input string, so this step runs in n time. These 3 steps together make up the computational backbone of the solution. Now, combining the time complexities of the 3 steps, we get n for counting frequencies, k log k for sorting, and n for building the result string. Adding these gives O n plus O k asterisk log k plus O n, which simplifies to O n asterisk log n, in the worst case because k is always less than or equal to n. Moving on to space complexity, the counter object frequency stores the frequency of each unique character, which requires O k space where k is the number of unique characters. Similarly, the sorted _chars list, which stores the sorted order of the unique characters, also uses O k space. Finally, the result string requires O n space, as it has the same length as the input string. Adding these together, the total space complexity is O k plus O k plus O n, which simplifies to O n, because k is always less than or equal to n. This illustrates that the solution is efficient in terms of both time and space. When considering the best, average, and worst cases, the time complexity remains consistent at O n asterisk log n. This is because the fundamental operations, counting frequencies, sorting, and constructing the result string, are directly tied to the size of the input string and the number of unique characters, without significant variation between cases. To put this in perspective, a brute force approach that generates all possible orderings of the characters and sorts them by frequency would result in a time complexity that grows factorially, such as O n. In contrast, the optimized solution leverages efficient frequency counting and sorting, reducing the time complexity to O n asterisk log n. Mathematically, this is supported by the dominance of the sorting step, which operates in O k asterisk log k and simplifies to O n asterisk log n, since k is at most n. By combining these with the O n complexities of the other steps, we see that the solution balances both time and space efficiency, making it well suited for the problem constraints. When tackling this problem, it's important to be aware of some common mistakes that can trip you up. One major issue is ignoring edge cases. For example, consider inputs like an empty string, a single character string, or a string where all the characters are the same. If these cases aren't handled properly, your code might produce runtime errors or incorrect results. The solution is simple: make sure to test your implementation with these edge cases to ensure it behaves as expected. Another common mistake involves calculating frequencies incorrectly. This can happen if you misuse dictionary operations or fail to update counts accurately, which results in flawed frequency mappings and ultimately leads to an incorrect solution. To avoid this, leverage built-in tools like Python's collections, counter or equivalent hash maps in other programming languages. Additionally, sorting inefficiently is another pitfall. Sorting the entire string instead of just the unique characters is unnecessary and increases the time complexity of your solution. Instead, focus on sorting only the unique characters based on their frequencies for a more efficient approach. Another frequent issue is overcomplicating the solution. For instance, some might use nested loops or introduce additional data structures that aren't actually needed. This approach can increase both time and space complexity, making your solution less efficient. To address this, always aim for a clean, straightforward approach that directly aligns with the problem's requirements. Also, it's vital to consider how to handle ties in frequency. If two or more characters have the same frequency and you don't specify a way to resolve these ties, the output may become inconsistent, potentially violating the problem's constraints. A good fix is to implement a secondary sorting condition, such as sorting characters with equal frequencies in lexicographical order. This ensures that your solution is both predictable and correct. Now, let's think about how this problem relates to interviews. Problems like this often fall into the broader category of frequency counting, sorting, or heap-based prioritization. The optimal approach generally involves using a hash map to count the frequencies, followed by sorting based on those frequencies. For scenarios with very large inputs, you might want to consider heap-based sorting to balance memory usage and performance. Speaking of performance, it's important to understand the time complexity trade-offs. Brute force methods, which might involve repeated operations, can run in O n squared, while optimized solutions combining a hash map with sorting can achieve O n log n. For even better efficiency, you can aim for O n log k by using a heap, especially if you only need the top k frequent elements. During interviews, it's crucial to communicate your thought process clearly. Explain the trade-offs between time and space complexity and justify why you chose a particular approach. Recognizing related problems, like LeetCode 347 for top k frequent elements or LeetCode 692 for top k frequent words, can also help you identify patterns and build confidence. There are also several alternative approaches worth exploring for this problem. A heap-based approach, for instance, is an excellent choice when you're only interested in the top k frequent elements. It avoids sorting the entire dataset, bringing the time complexity down to n log k. This is particularly beneficial when k is much smaller than n. Another option is the bucket sort approach, which achieves linear time complexity, n, by grouping elements into buckets based on their frequencies. However, it does require extra space to store the buckets, so it's most effective when the range of frequencies is small relative to the input size. Finally, for more specialized scenarios, you might consider using custom data structures like a tree. This can be useful for problems involving hierarchical sorting or additional constraints, such as maintaining lexicographical order. While it's not the most common approach for this specific problem, it's worth keeping in mind for cases where frequency counting is just one part of the challenge. Great work! To summarize, we solved the problem by counting character frequencies and sorting them efficiently. Remember, mastering problems like these sharpens your understanding of core concepts like hash maps and sorting. Keep practicing, and don't forget to check out more problems to continue improving. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!